Hello, this is Susie Newhan, and this is the one about present value and the time value of money. Okay, time value of money. I'm going to start with a question. I think we all know the answer to that, but what about this one? A little less clear, isn't it? Because we have to think about things, well, I don't know about inflation, there's a lot of uncertainty. I don't know whether the other party will renege on the agreement and whether I'll actually get that money if I decide to take it later, so perhaps I'd better take it now. But for the rest of this video, we're going to be assuming that we are operating in a risk-free environment. We're going to assume that inflation is constant, and we're going to assume that everybody keeps their promises. So that's what we have to think about. So given that, we're not really sure how to answer this. So we have to put away that emotional response of just prepping it now. All right. So what we're going to be learning about today is this thing about how do I assess what an amount of money that I have to wait for is worth to me now. Okay, so there's always this idea that we have to wait for something, and is it worth waiting for, is the question. And there's always an assumed interest rate, which is sort of tied in with your cost of capital, inflation, but you don't have to worry about how we make up the number. That's always going to be given to us. If you're an analyst in a company, your financial director would tell you what interest rate you should assume, because it's to do with how much a company has to pay for the money it borrows and all sorts of things, market conditions stuff. But we don't have to worry about that. We will always be given an amount. There's this idea, isn't there, and I think we sort of know it intuitively, that money we get in the future is worth less to us than money we get now. It's not just delayed gratification, there's other stuff going on there as well. So first of all, an important point in finance is that if we're going to compare two costs or two benefits, two bonuses or whatever, we can only make that comparison if we're doing it at the same point in time. Okay, this is sort of Back to the Future stuff. You remember the movie? You can't compare an amount in a bank account in the 1950s with the same amount in the 1980s. There's just no comparison. So we're having to come up with a framework where we can make a comparison. So here's a little notation. So we've got the present value. Present value is a sort of fairly easy concept to understand. It's the amount that something is worth now. So present always means now. And then we've got this future value. And so we're going to be doing a lot of comparing between present values and future values. And future values is this amount, which is usually bigger than the present value, that we get at some point in the future. And here's an important word, indifference. We are looking to find the amount of money at the future end that would make us indifferent between the two. Because remember, I said we assume that payments are going to be made in the future. We have no worries about that. So we're looking for this idea of indifference. I don't care whether I get the money now or in the future, because the future amount is compensating me for the fact that I have to wait for it. All right, so this indifference idea is very important. So why is money we receive later worth less to us? Well, fairly obviously, if we have to wait for the money, we are missing out on interest that we could be gaining now. If we get the money now, we slap it in the bank and we start earning money. So mostly by accepting a future value, it needs to be big enough to compensate us for the loss of that interest. And we're leaving out inflation here, because inflation is going to be factored into interest rate. All right, so that's the notation. And this process of finding the present value is about looking at a future value and working out what it is worth to us now. And then we can compare it with other schemes or projects or other future payments. Okay, but it's this idea of getting everything into the present value. Okay, so let's look at one amount. We're looking at a present value of $1,000, and we're going to have it at 10%, and we're comparing what it would look like a year later. So if we put 1,000 in the bank now, in 1 year it would be worth 1,100. You'll remember from our percentage that we did together. So we are saying that we should be indifferent between those two amounts. We would either take 1,000 now, or we will take 1,100 a year from now. We don't care. They are the same amount to us. So we learned, didn't we, in our compound interest studies, that that the future value can be calculated from the present value, or the principal amount, the amount we have now, if we multiply it by 1 plus the interest rate raised to the power of t. That's our compound interest formula. All right, and we learnt that R is the interest rate. We can think of R as the return. And so if, just as a reminder, if we're at 5%, then R is going to be 0.05, and 1 plus R will be equal to 1.05. That's our compounding factor. All right. So how would we find the present value of an amount in the future? That's what this video is mostly about. Let's get to the crux of it. So the future is coming. We have to be able to assess it. So let's start with this. Hopefully you're familiar with this. If we have £1,000 at 10% over 3 years, we're going to multiply 1,000 by 1.1. That's going to add 10% to it. So at the end of the first year, we've got that amount, and then we multiply by 1.1, which is like adding 10%, adding that 10%. And then we get this amount, and then for one more year, we multiply it by 1.1 to get our final amount. So that is just us using the compound interest formula. And of course, R here is 10%, so it shows up as 1.1. All right, so hopefully all well and good. So maybe there's a little bit of hint here about how we might calculate the present value of a future value. So this is finding a future value from a present value. That's what we've been doing at school for years. Now we have to look at it the other way around. So let's explore this a little bit. So we can also ask, so this is important. We might ask, let's suppose we don't know this. All we know is that we get this 1331 in the future. We might say, well, what would I have to put in the bank 3 years before to get that amount later? So that would be telling us how we work out our present value from a future value. So let's look at that a little bit. This is the end point. We know we want that in 3 years' time. So how much do we have to invest now? Let's pretend we've forgotten. All right. So here, in that last year, we took an amount and we multiplied it by 1.1 to get 1331. So hopefully you can see that we could work back to that number if we, instead of multiplying by 1.1, divided by it. And if we divide that amount by that, we know we're going to get that. That times that equals that, so that divided by that is equal to that. It has to be. So let's do that again. And it seems like at the end of the first year, we'd have to invest that much to get there in order to get there. And let's go back one more year and we'll see how much we'd have to put in the bank now, in the present. So let's divide by 1.1 one more, and what a surprise, we get 1,000. So we have just worked out what the present value is of that future value. Okay, just before we move on to the formula, just a quick reminder about a little algebra. Right, if we have 25x times 75, we know what 25 lots of x are, but we don't know what one lot of x is. So how do we get it down to one lot of x? Well, we could divide both sides by 25. We can divide each side by anything we want, as long as we divide each side by the same amount. We are going to divide by 25. So what will we get? We will get x over 70, x equals 75 over 25, so x equals 3. All right, so what about something like this? Well, that works in just the same way. We want to get x on its own, so we're going to divide both sides by this, which looks a bit like a compounding factor, doesn't it? It will disappear from here and just end up there. So here we go, 8, 0.1 plus 0.1, okay? And one more, which is almost identical, except it's got a power. If we want to get x on its own, we're going to have to divide both sides by this, so it disappears from here, and it will end up on this side, 1 plus 0.05 to the power of 3. So we can divide by compounding factors just like we can any other number. All right, so we're on our way to the big formula. All right, so a reminder of the one we've had before. If we know the present value and we know the interest rate, we can find the future value. So we've been doing that for years. So what happens if we divide both sides by 1 plus r to the power of n, the compounding factor? We get that. And let's just turn it around because it looks better that way. So there it is. We can find, very simply, the present value of any future value by dividing it by the same compounding factor. And it's as straightforward as that. So there it is. There's our wonderful formulae. And, you know, the future's back. We brought the future back to the present. So let's just remind ourselves of this. Remember, we were likening finding the future value from the present value to finding the future value into the present value. And here's our new equation, our new formula. And here we found that 1,000 by dividing the future value by 1.1 raised to the power of 3. Because look, we divided by 1.1, divided by 1.1 again, divided by 1.1. So this is like dividing by 1.1 to the power of 3 because we're doing that division 3 times. So we are getting there. So this is what the framework looks like. If we go from the present value, to the future value, then we multiply by the compounding factor, just like we've always done with compound interest. But if we want to go to the future, back to the present, we do this process called discounting, which is where we divide by 1.r to the power of t. So the calculations are pretty similar. This is a multiplication, that's a division. So let's have a go. Let's see if we can use it. Okay, you've got an eccentric aunt, used to be a banker, accumulated quite a bit of money. She's left you some money, but she likes to have her little joke at the end. So the catch is that you've got 5 minutes to decide whether you're going to take 50,000 now or 60,000 in 5 years. So it couldn't be more real life than this. Your money depends on this. So what do you do? Well, the solicitor, nice chap, lends you a calculator and tells you that you might want to think in terms of 3% over the next 5 years. So can you see the framework is such that we need to decide, are we going to take 500 now or are we going to wait 5 years and get 60,000? Again, we don't have to worry about whether it would actually happen. We have complete trust in that. Inflation has already sort of factored into that 3%, so we don't have to worry about inflation. So which would we choose? So there are options, A and B. And we're going to calculate this from 2 angles. You don't have to do 2 angles, but it helps you sort of understand what we're doing. You can choose. So here's our choice. A is 50,000 now or 60,000 in 4 years' time. Those are the 2 options that we have to choose between. We've been given a discount rate by the solicitor. So how do we work out what the future value, what that value will be worth in 5 years at? Well, hopefully you can see that it's going to be 50,000. And we're just going to use compound interest at 3% raised to the power of 5 because we're looking at 5 years. So there it is, done for me. All right, so we could actually stop now if we wanted. We could say, oh, look, the future value of this is less than that, so take option A. So in this case, we've got both amounts in the future at the same point in time, 5 years' time, so we can make a direct comparison between them. So that would be enough, really. But it's conventional to put everything into present value. So if you're looking at a lot of incomings and outgoings, it's traditional that we bring it all to the present value so we can make a comparison. So let's do that, and we'll give us some extra practice. So the next question then, let's supposing we haven't done that, is we want to know what that amount is worth in the present value. So how do we do that? Well, we use our new handy dandy formula. And that tells us that future value equals, no, wrong way around, present value, which is what we're looking for. Yeah, we know the future value, it's the present value we want. So this is at 3% for 5 years, and we know the future value in this is 60,000. So this is going to give us that amount. And there it is. So even if we hadn't done that, we can now look at these two and say, well, this option is obviously better. We should take B. We should have the courage of our convictions and wait 5 years. Present value, future value, worth more. Yeah, so this is worth more than that. Therefore, we'd pick this one. All right, let's do another one. Okay, so now we're being offered. This is possibly not your aunt. We're being offered 50. So maybe buying a public limited company or something. We've got the choice between 50 billion now or 63 billion in 7 years. Be awfully tempting to take that 50 billion now, wouldn't it, regardless, at 2.5%. So we want to know what that 50 billion is worth in 7 years' time. So we'll do it both ways again because it's good practice. So the future value of that, future value is equal to the present value, 1 plus r to the t. So the present value is 50 billion, 1 plus 0 to 5, 2.5%. So we need that placeholder of the 0 there. Remember, the first 2 digits after the decimal place tell you the number of whole percent, to 7. So that is 59.4 billion. So we can already see which option we should take. But let's do it the other way as well, because it's good practice. All right, so we know that the future value is that. So we are now going to use the other formula, which says if we know the future value, we can calculate the present value by dividing by the compounding factor. And we know the future value here is 63 billion. So if we calculate that, we will find what it's worth now. And there it is. So we can see it doesn't matter if we look in the future or the present, both of them point to the same conclusion, that A is a better option. No, that B is a better option. Take that back. B is a better option because the present value of option B is bigger than the present value of option A. But also if we look in the future value of option B is better than the future value of option A. It will always be the same. If it's bigger in one, it will be bigger than the other. And just one more. Is it worth doing one more? Just very quickly. 7.2 million in 10 years' time is worth this. So this is better. Option A looks better here, doesn't it? But let's also look into, take the future into the present. There we would be dividing by the compound factor. And so we see here also that option A is better because the present value of option A is bigger than the present value of option B. And finally, just here's a nice chart which shows you what difference the varying interest rates actually makes. So the idea is here, this is what £1 is worth a certain number of years from now. So for instance, if we were looking at 5%, so £1 received, say 10 years from now, is worth in present value terms, about 0.65. So it degrades quite a lot. We're experiencing interest rates of 5% and we wait 10 years, our £1 is only worth 65 pence on the pound. But look what happens when interest goes up. And I've lived through, because I'm so old, I've lived through inflation rates of 20%. Pretty scary time. And look how much, if you have to wait 10 years to get your pound, and you want to know what that's worth in present value terms, well, it's only worth about, I don't know, 15 pence. So the level of interest makes a huge difference to these analyses. So here's some practice questions. I'll slowly reveal the answers, so freeze frame when you want to work on the questions. And here's some other questions.